All right, now we're going to look at the magnetic field of a current loop. So I pulled this figure from our book, our e-text. The loop, so a loop of current, a ring of current. Now realistically, we probably wouldn't have just a single ring like this. If we had a wire coming in to make a ring, it would have to then exit somewhere to go back to the battery to have current flow. Or we could have the wire turn and loop and keep going that way, that type of thing. So seeing the full ring may not be the full picture, I suppose. When we have a current loop, though, thinking about the right-hand rule, when we put our thumb in the direction of the current and our fingertips show which way around the current loop, the magnetic field is circling. In this left-hand picture, right here, that dot inside the ring represents that current is flowing out towards us in that portion of the ring. And so it's as if we're looking at a cross-section of the ring from the side. The X down here is the current going in to the ring. So at the top, if we put the thumb of our right hand pointing out towards us to represent the current, our fingertips are rotating or showing counterclockwise around our thumb. And so we see these little arrows on the left side going down, on the right side coming up, representing these counterclockwise circles around the ring. Similarly, on the bottom, if we put our thumb away from us, point our thumb in towards our screen, our fingertips go down on the right, which then would come up on the left and show counterclockwise circling. So the magnetic field of this loop ends up passing through the loop to the right, circling around and coming back in to the left, on the left side. So again, the magnetic field is continuous. There's no starting point or ending point. They just loop all the way around. Now, similar to when we were looking at electric fields, in this region where these the magnetic field lines are really close together, represents a much larger strength of magnetic field than outside here where these lines are farther apart. So closer lines represent a stronger field. If the lines are farther apart, the magnetic field is weaker. The middle picture is just a different viewpoint, looking at the ring as if we were on the right side in the first picture. So we would see all those magnetic fields coming out towards us inside the ring, and then looping around, we'd see them going away from us on the outside of the ring. But they would make complete loops around the ring itself. It's just hard to draw those loops from this middle perspective. The right-hand picture is a ring with current flowing through it with just iron filings to line up with the magnetic fields. And so we can see that magnetic effect on those little pieces of iron. Now, to determine the strength of the magnetic field, so we're going to first of all, the Biot-Savart law that we use to find the magnetic field due to a long straight wire still applies. So as a reminder, we need to treat the wire as a bunch of little pieces carrying current. So the ds represents the length of the little piece. I is the current flowing through each little piece. R itself is the distance from this loop to the point we're interested in, which I'm going to draw a picture. We'll talk about that. And then r hat is just the vector that lies along that line. In terms of the magnitude, if we want to find the direction ourselves using the right-hand rule, with any cross-product equation, we can take the magnitude of these two vectors times the sine of the angle between them. And this will give us the magnitude. So I'm going to write this, mu naught times I. ds is just going to be the magnitude of the length of the little piece of wire that we're going to talk about. The magnitude of r hat is just the number 1, because it's a unit vector, so it has a length of 1. Sine of phi. Phi, remember, is the angle between the ds vector and the r hat vector. So we're going to draw that and figure that out as part of our problem. And then over 4 pi r squared. And then our limits, we're going to need to get everything in terms of the same variable, and our limits will just be where the ring is located. So let me scroll this up a little bit. We're going to look at our ring. I'm going to try to draw kind of a view from the side. We're going to solve this first for the B on the axis of the ring or loop. So if we look in the picture above, the axis of the loop is the line that goes straight through the middle. So that's what we mean. So I'm going to draw a line representing this axis. And we're just going to call this the z-axis. So we're going to try to find the field at some point over here. Now this is the magnetic field specifically. So the magnetic field is caused by current flowing around the loop. So we could think of this loop as a whole bunch of little infinitesimally small pieces of current, I. The length of each piece, the length of the piece, we're just going to call ds at the moment. The direction of ds is just the direction that the current is flowing. And I'm going with the direction of the loop above. And so we need to add or sum the magnetic field due to each of these pieces. We're going to call the radius of the ring itself capital R. So the capital R is the radius of the loop or ring. In our equation, though, for calculating magnetic field, the R we want, I'm going to choose this piece down here, is the distance from this piece of wire out to the point we are interested in, where we want to calculate the strength of the magnetic field. So this R makes a triangle where we have the radius of the loop itself and some distance along the axis, which I'm going to just call the z distance. So z is the distance along the axis where we want to find the field. So we can say the distance from our piece of current to that point, just using Pythagorean theorem, would be the square root of capital R squared plus Z squared. Now, as we think of each little piece of current and think about the distance to this point up here, this distance is going to be the same for every single piece of current because the axis goes through the middle of the loop. So each piece of this loop is the same distance away from a point on the axis. So this is actually a constant for each piece, meaning there's nothing in this portion that needs to be integrated. Coming back up to our equation, phi in here is the angle between ds. ds is tangent to the loop. It's the direction the current is flowing in. And then r hat, it just lies along the line of this r that we just talked about. Phi is 90 degrees because r hat points directly away from the loop up to this point. I'll just call it point P. But the current flows through the loop, and so they make a right angle with each other. So sine of 90 stalling a little bit on me. So sine of 90 is 1, which means our equation over here for the magnitude specifically, the magnitude of the magnetic field, mu naught is a constant, I is the amount of current flowing through the loop. I'm still calling this ds for now. Sine of phi in this case is just 1 over 4 pi r squared. And we know r, so if I put that in here and square it, this is where we're at. Now this would represent the magnitude of the magnetic field. The magnetic field does have a direction associated with it. I don't know if you recall, but in a cross product equation, which we have, when we are saying the magnetic field vector, the direction is determined by the cross product of ds crossed with r hat. The result is always perpendicular, so this magnetic field is going to be perpendicular to both ds and r hat. Now, if we use the right-hand rule and put our thumb in the direction of the current, I'm going to change my color. Putting my thumb in the direction that kind of points down and towards the bottom of the loop, my fingers, the general direction of my fingers is pointing this way. It has to be perpendicular to r hat, and r hat lies along r. So our magnetic field is going to have x and y components and z components. But if we think of a corresponding piece of charge or piece of current in the wire that's exactly opposite this same current, its magnetic field will point, let's see, this way, perpendicular to its r. So if I was to draw in the little r, I didn't get that perfectly perpendicular, but it would point off such that the x and y components cancel. which that's what we see in this picture above. If I kind of erase my lines along this axis, the magnetic field is completely pointing to the right. It's completely pointing in this Z direction. And so we only need to account for the Z components of the magnetic field. So on my equation over here on the right, I'm going to put a Z, and then we need to make sure we can figure out what Z is, the Z component. So I'm going to call this angle up here theta. The Z component would be the magnitude of the magnetic field times the cosine of this theta that I've drawn. So theta just represents the angle between the magnetic field and the Z-axis. So my equation over here on the right needs a cosine theta because this portion represents B, the magnitude, which we're going to integrate in a minute. But I need to multiply by cosine theta to get the Z component. So that when we integrate, our integration will account and add up all of the Z components that are created by every portion of this loop. All right. The corresponding piece of charge will make the same angle. If I think of any of these pieces of charge, any of these pieces of current, they will all create a magnetic field strength that's the same, and that magnetic field vector will make the same angle theta with the Z-axis. Now theta up here, if I come down to my loop, it's the same as the angle between the plane of the loop, so between the radius of the actual loop itself and r, lowercase r. So if I think in terms of my triangle that I have, and this is my theta, cosine of theta is going to be the adjacent side, which is capital R, the radius of the actual loop itself, divided by lowercase r, the distance to point P up here. And we've already determined that lowercase r is the square root of capital R squared plus C squared. So if I come over and put this in place of cosine theta, I put in capital R over the square root of R squared plus C squared. This becomes the overall integral I need to solve to find the magnetic field on the axis of the loop. Now let's think about what's changing. So when I look back at my picture, I'm accounting for all of these little pieces of current. So I'm imagining my loop is made up of a whole bunch of little pieces of current. All of them are contributing to the magnetic field at point P. All of them are going to have the same current. So when I look at my actual integral so far, they're going to have the same current. Mu naught already is a constant. ds just means the length of each piece. That's going to be the same. We're assuming we're cutting this loop up into a whole bunch of similarly lengthed pieces. Capital R means the radius of the loop. And since we're talking about the axis in the middle, each piece of current is a distance of r from the center. For pi is a constant. Z is also a constant because Z means the distance, if I come back to my picture, from the center of the loop out to the point P that I'm interested in. What that means is I can pull out mu naught, I can pull out I can pull out R. In the denominator, I can pull out all of this stuff. I am going to combine these quantities of r squared plus z squared. So I have it to the 1 power and then the square roots to the 1/2. So when I combine these, I get the r squared plus z squared to the 3/2 power. And I'm suddenly left with just the integral of ds. So what this means, so just thinking about my loop, in order to account for every piece of the loop, let's say I start up here, and I want to add all of these little pieces of current all the way around, my limits of integration are going to be from where I started, which I'm just calling 0, to how far I've traveled to get all the way back to here. So 2 pi r is the distance I have to travel to account for every single piece of this loop. So ds just represents a length. So when we have integrated, you can think of it as an S final minus S initial. How far did I travel to end up closing the loop? So we end up with mu naught I r times 2 pi r over 4 pi r squared plus z squared to the 3/2 power. And of course, on top, we can combine, we can simplify and end up with the 2 in the bottom. And then r squared, because we end up with that capital R times the capital R, to the 3/2 power. Now, this equation is in the test notes called B of a loop. This represents the magnetic field specifically on the axis, the line that goes through the center of the loop, a distance of z away from the center of the loop, and capital R represents the radius of the loop itself. I is the amount of current that is flowing through this loop. So this loop doesn't have a net charge. So we talked about a loop with the electric field where the loop had to have a net charge, and then we could find the electric field. Here, the magnetic field is only created if there is a flow of charge. So current, the charges must be moving around that wire in order to create this magnetic field. We can always determine the direction based off of the right-hand rule. If we consider any portion of the loop and consider the current flowing through it, so for example, at the very top of our loop, our current was flowing towards us. So if I put my thumb in the direction towards me, underneath that wire, my fingertips point to the right. ultimately, the magnetic field makes circles around this loop. And my fingertips show me which way those circles go. It turns out with a loop, we can interchange our thumb and fingers. So far we've been looking at putting our thumb in the direction of the current. If the current is looping, it is valid to take our fingers to follow the current loop. So the current that is looping, it has to be going in a circle to do this. So the current that is looping, I can take the fingers of my right hand and let them follow the loop of the current. My thumb represents the magnetic field direction in the center specifically. So it's kind of just the inverse of what we've been doing, where we put our thumb in the direction of current, our fingers represented the direction that the field looped around the current wire. We can put our fingers in the direction of the loop and go from there as well. And then our thumb will be the direction of the field, but specifically in the center. Okay, so B of a loop, you don't have to derive it again because this equation right here is in the test notes. The next equation you're going to see, just to build on this, is called B of a coil. I'm not entirely sure why our author splits these two up. B of a coil simply means B, the magnetic field strength, in the center of the loop. So same loop, it still has to be carrying current. The Z axis still goes through the center, but for the coil, we're essentially saying that Z is 0. So we're looking for the field strength right smack dab in the center of the loop. So this equation, if Z is 0, this now is called B of a coil. So we have the mu naught I r squared over 2 r squared plus 0. So we get mu naught I r squared over 2r cubed. One of the r's cancels, mu naught I over 2r. Now this is slightly different when you look in the test notes as well as in the textbook. You're going to see this. See an N. Now if you think about it for a sec, I imagine it will make sense what N means. So our loop up here, we were talking about a wire that just looped around once. And so this equation allowed us to find the strength of the magnetic field due to that one loop of wire. And when we plug in 0, we of course get the equation in the smack dab center of that one loop of wire. But it is totally common and possible that we might have a wire that loops around a couple times. I don't know if that even makes sense now. So my wire comes, it makes one loop, but then it turns again and makes a second loop, turns again, makes a third loop. So N is representing the number of loops or turns of the wire. Now this is limited because we do have to assume that each loop has the same radius and essentially the same center. So this only works for very tight loops and only for a few of them. Because if we start looping more and more and more and more and more, They can have the same radius, but they're certainly not going to have the same meaning of z equals 0. And that's the assumption we've used in getting to this equation. If we have lots of loops like this, we call this a solenoid, and we're going to get that equation in a minute. So if you use this B of a coil, it has to be in a situation where we know the loops are very tight and close together, such that we have the same radius and z equals 0, essentially at the center of all of them. So that's why it just needs to be very tightly close together, just a few loops, and this will work. All right, one last thing to go along with this. Let me grab our picture up here. Oh, maybe it won't let me. Let me grab the picture again. Give me a sec. All right, so I pulled this picture from our book again. One last thing to talk about with this. When we look at this current loop magnetic field in here, so these blue lines are representing the magnetic field created by this loop. They wrap around. They go to the right through the middle of the loop, wrap around, and go all the way over to the left outside the loop. So they both come in and out. They're continuous. Now, if we think about a bar magnet, let's think about a really skinny bar magnet that has a north and south pole. As we mentioned in an earlier video, magnetic field lines come out of north, they wrap around, come back into south, and travel south to north within the magnet. So essentially, if I took the magnet away, I would see, not away, but out of my picture, just to see my picture better, I would see these magnetic field lines looping around. Essentially, they would look the same as this loop, or extremely similar. When we have a bar magnet, I'm going to draw it bigger, south to north, and we talk about the magnetic field looping around and continuing inside, south to north, exiting the North Pole, coming back in at the South Pole. The inside portion, so inside, we call this a magnetic dipole moment. Now, you'll see this as a mu in the test notes. This is the symbol our author used originally, and it's the common symbol we would see. But as I was looking in the e-text, they have changed and decided to call this a lowercase m, which to me makes sense because we have mu naught, that's a constant. And so it could be very confusing to see mu and want to use the constant versus not. So test notes versus book, you're going to see mu as the magnetic dipole moment. If you're looking in the text, they're using a lowercase m. I will try to remind you every time we talk about it, which is that they're the same thing. So every permanent magnet is going to have its own unique mu, its own unique magnetic dipole moment. When we talk about it for the coil, though, the coil or loop is a magnetic dipole moment. So we can talk about it in terms of mu or M. It turns out that we have B of a dipole, whether we're talking a coil or loop or our permanent magnet, doesn't matter. The magnetic field of a dipole, this equation assumes that we are very far away, so Z is a lot bigger than R if we're on the loop. So essentially, if we come down to my permanent magnet that I've drawn, this equation, B dipole, is for on the axis, so the line that the dipole moment would lie along, but far, far away from the magnet, such that the length of the magnet is insignificant compared to Z. The equation looks like this. Mu naught to mu, meaning dipole moment, over 4 pi Z cubed, where Z is this distance from the magnet, which essentially looks like a point because we're so far away. Not in my picture, but that's the assumption as far as using this equation. So distance from the magnet out to the dipole. Or in the loop, the distance from the loop out to where you're measuring the field. But Z has to be much larger than R. If we compare this, actually, let me do this really fast. In terms of using the lowercase m as the magnetic dipole, the same equation would look like this. It would have the m instead of the mu. So mu or m is the magnetic dipole moment. If we compare this equation, I'm going to scroll just a little bit to what we were deriving up here for our coil. Let me see if I can lasso you. And bring you, oh dear. Okay, I'm going to do it this way. So I intentionally grabbed the step before because pi r squared is A. So the cross-sectional area of the loop, and then I would still have 2 times I over 4 pi, but again, we're making the assumption that Z is a whole heck of a lot bigger than R. If that's the case, the R squared term is insignificant. It's essentially 0 compared to Z, and so that leaves me with the Z cubed. If I compare this to what we just said is the field for a dipole, I find that the dipole moment, mu, or lowercase m, whichever way you want to write it, is equal to I times A. The current times the area of the loop. So this is specifically for the loop. the loop area, gives me the magnetic dipole moment. And then I could use this equation up here if I'm looking for the magnetic field along the axis very, very far away. Now, this does assume only one loop. As we mentioned before, we could have a couple loops, 2, 3 loops, very tightly wound. If that is the case and we want to account for them all, we would just want to add to account for however many loops we had, how many numbers of loops. And then this top equation would work. So to summarize, the main equations we have at the moment on the test notes for wires. We have B of a wire, mu naught I over 2 pi d. This was for a long, straight wire. This finds the strength of the magnetic field anywhere around the wire, where d is just the distance from the wire to the point where you're finding the magnetic field. We showed this and used this in previous videos. This video, we've talked about B of a loop. Just writing it out again. I had the r squared before the z squared, but the addition order doesn't matter. That's all under the square root sign. This is for a single loop of wire somewhere along the axis that you're trying to find the magnetic field. B of a coil is just at the center of the loop. Center of the loop, meaning z is 0. And then n is accounting for the number of loops or turns of wire. And then B of the dipole is for either a bar magnet with a magnetic dipole moment that's hard to read, moment, or not a coil, but a loop where Z is a lot bigger than R, so that this magnetic dipole moment is simply I times A. Because the magnetic field looks like that of a bar magnet in this situation. So these are the main equations for wires carrying current, and then the magnetic fields that they create. We're going to talk about a solenoid next as well, which is another common element. And then we'll start talking about interactions with different moving charges, that type of thing.